Hello, grade 10s, and welcome back to another lesson on electric circuits. In this lesson, we will be focusing on series circuits. So we'll be zooming in on circuits where the resistors are connected in series. We're going to start off by looking at the different rules of series circuits and how circuits work when the resistors are connected in series. And if you know all these rules and you follow all these rules for a series circuit, you cannot go wrong. So the first rule tells us that the total resistance, now please keep in mind that if you're asked to calculate the equivalent or the effective resistance, it means the same thing as total resistance. In a series circuit, you may calculate the total resistance by adding up the resistances of the individual resistors. Remember that resistance is measured in ohms, and resistance is represented by the letter R. So the total resistance in the circuit can be calculated by adding up the resistances of the individual resistors. So if in a circuit I have a 2 ohm and a 5 ohm and a 3 ohm resistor, then RT equals R1 plus R2 plus R3, which is 2 plus 5 plus 3, which is 10 ohms. Now, what we can see from that is that the more resistors we add in series, what happens to the total resistance? Well, it gets higher. Because if I added another resistor in series, I would simply be adding it to this formula over here, and I would get a different, higher total resistance. Now, in any circuit, the voltage is provided by the cell. Remember that voltage is the energy per unit of charge, and the cell provides that energy to push those electrons into the circuit. In a series circuit, we may calculate the total voltage by adding up the voltages across all the individual resistors. That is assuming that we haven't been given the voltage of the cell. So if I'm told that in a circuit that's set up in series, I have two resistors, one with a voltage of 2 volts across it and one with a voltage of 4 volts across it, then I can say that the total voltage is V1 plus V2, which is 2 plus 4, which is 6 volts. And that would then apply to the total voltage of the cell or the battery. So however much voltage the cell provides to the circuit, the voltages used up across all the resistors will be equal to the voltage of the cell. It will never be more than, and it will never be less than, the total voltage of the cell. If the resistors are identical, the voltage will divide itself equally across the resistors. Remember that resistors are like obstacle courses, and voltage is the energy needed to get through those obstacle courses. So if the electrons, moving electrons, are the current, so if those moving electrons are going to move through two resistors that are identical, then they are going to share their energy equally among those resistors. If a resistor is stronger than another resistor, well, more energy, more voltage will get used up across a stronger or greater resistor. So if the resistors are not identical, a resistor that has a higher resistance will have a greater voltage across it, and the resistor with a lower resistance will have a lower voltage across it. And that makes sense, because if you've got a harder obstacle course to get through that is equivalent to a higher resistance, you are going to need more energy to get through it, and that's equivalent to a greater voltage. So because of this, series circuits are known as voltage dividers. Why? because the voltage gets divided among the resistors in the circuit. So if you're ever faced with a question where they talk about a voltage divider, what they're really talking about is just a series circuit. Now, in any circuit, the relationship between resistance and current is inversely proportional. Let's consider this relationship between resistance and current. Now, remember that Ohm's law tells us that R equals V over I, so resistance can be measured as voltage divided by current. Now, this formula may be rearranged as V equals IR and I equals V over R. Now, by looking at a formula, we can identify relationships between any two variables, provided that the third variable remains constant. So what do I mean by that? So if I want to see the relationship between voltage and current, then the resistance must be kept constant, meaning that the value for the resistance shouldn't change. Then we can zoom in on the relationship between voltage and current. We will keep our resistance constant at a value of 2 ohms. So if my current is 1, then my voltage will be 2. But if my current increases to 3, then my voltage will be 6. And if my current now decreases to 2, then my voltage will be 4. So what's the relationship between voltage and current? Well, voltage and current are directly proportional, because as the current goes up, the voltage goes up, and as the current goes down, the voltage goes down, and that's again assuming that the resistance has been kept constant. And we may also refer to it as the voltage being directly proportional to current using this symbol. This symbol means directly proportional. Now let's look at the relationship between voltage and resistance, keeping the current constant. So here we're keeping the current constant at 3 amps, and we're going to change the resistance and see how the voltage changes. So if the resistance is 2, then the voltage is 6. And if I increase my resistance to 4, then I increase my voltage to 12. And if I decrease my resistance to 3, then I decrease my voltage to 9. And again, we can see that there is a directly proportional relationship, because as resistance goes up, voltage goes up, and as resistance goes down, voltage goes down. So voltage and resistance are directly proportional. So what we've just seen is that the relationship between resistance and voltage is directly proportional, and the relationship between current and voltage is directly proportional. And by rearranging the formula, we don't destroy that relationship unless we've rearranged our formula incorrectly. So here we can see that resistance and voltage remain directly proportional. And here we can see that current and voltage remain directly proportional. So if I keep my current constant, and I keep it constant at a value of 2, if the voltage value is 2, then the resistance value will be 1. And if I increase my voltage to 4, then I will increase my resistance to 2. And if I increase my voltage to 6, then I will increase my resistance to 3. And if I decrease my voltage back to 4, then I will decrease my resistance back to 2. So we can see that the directly proportional relationship between resistance and voltage still applies. Let's relook at the relationship between current and voltage, keeping the resistance constant. Now I'm keeping the resistance constant at 3. So if my voltage is 1, then my current is a third, which is 0.33 amps. And if I increase my voltage, to 2, then my current will be 2/3, which is 0.67 amps. So the voltage has gone up and the current has gone up. And if I increase my voltage to 3, then my current will go up to 1. And if I decrease my voltage back to 2, then my current will go back down to 0.67 amps. So again, we can see that there is a directly proportional relationship between current and voltage. Now, this is not going to sound very mathematical, but it is very useful to think of it like that. I think of these variables as being on the same line, or on the same plane, versus not being on the same plane. So over here, voltage and current are on the same line, so they're directly proportional, and voltage and resistance are on the same line, so they're directly proportional. Now here, resistance is still a numerator, as is voltage. So they're on the same line, so they're directly proportional. And the current and the voltage are on the same line, so they are directly proportional. And again, note that we don't destroy any of the relationships. We don't change those relationships by rearranging the formula. But if we've rearranged the formula wrong, then we would find differences in relationships, which would be wrong. But now if we consider the relationship between resistance and current, where resistance is numerator and current is denominator, or here, where the formula has been rearranged, where the current is the numerator and the resistance is the denominator, regardless, we can see that same type of relationship between them, where they're not on the same line. And that tells us that resistance and current are inversely proportional. And that relationship, of course, applies assuming that we keep the voltage constant. So let's take a look at this. Let's first look at R equals V over I, and I'm going to keep my voltage constant at a value of 10 volts. So if my current is 1 amp, then my resistance will be 10 ohms. And if my current increases to 2 amps, then my resistance will now decrease to 5 ohms. And if my current increases to 5 amps, then my resistance will decrease to 2 ohms. So we can already see that the relationship is not directly proportional, but rather inversely proportional, because as current increases, we can see that the resistance decreases. Now we can also decrease the current. So I can decrease my current back to 2 amps, and I can see now that my resistance goes up to 5 ohms. So we can therefore say that the relationship between current and resistance is inversely proportional. We can see the same relationship when we have rearranged the formula, again, provided that we've rearranged it correctly. In this case, I equals V over R, and again, we want to zoom in on the relationship between current and resistance. We're keeping the voltage constant at a value of 6. So if my resistance is 1, then my current will be 6. And if my resistance increases to 2, then my current will decrease to 3. And if my resistance increases to 3, then my current will decrease to 2. And my resistance can also be decreased. So if my resistance is decreased back down to 1, then my current will increase back up to 6 amps. Again, we can see that the relationship between current and resistance is inversely proportional. So what that tells us is that current and resistance are inversely proportional. Now, there is no symbol for inversely proportional, only for directly proportional. So if we want to use the symbol, then we've got to say that the current, I, is directly proportional to 1 over resistance, which is the same as saying that current is inversely proportional to resistance, Or we can say it the other way around. We can say that resistance is directly proportional to 1 over current. Or we can say that resistance is inversely proportional to current. Remember that Ohm's law applies to all circuits, whether they're connected in series or in parallel. I also want to bring it to your attention that whenever you're given a formula, you can identify relationships based on the way that that formula is arranged. So if I say to you that A is equal to B times C, and I rearrange this formula as B equals A divided by C and C equals A divided by B, what's the relationship between A and B? Directly proportional. What's the relationship between A and C? Directly proportional. What's the relationship between B and A? Directly proportional. What's the relationship between B and C? Inversely proportional. What's the relationship between C and A? Directly proportional. What is the relationship between C and B? Inversely proportional. If we look at F equals ma, that is a formula that we will learn in Newton's laws in grade 11. Force equals mass times acceleration. So without you even understanding it, if I asked you what is the relationship between force and mass, you would tell me that it's directly proportional. What is the relationship between force and acceleration? Directly proportional. Just don't forget that in all these examples that I've just mentioned, the third variable needs to be kept constant. Now we can come back to this with a better understanding. In any circuit, the relationship between resistance and current is inversely proportional. Now, in a series circuit, remember that as we add more resistors in series, the total resistance goes up. So therefore, what happens to the current? It has to go down. It decreases. Why? Because resistance and current are inversely proportional. In a series circuit, the current is the same wherever you measure it. So it doesn't matter where you place your ammeter to measure the current, you're going to get the same value regardless. So we say that the total current is equal to the current at any point in the circuit. Let's now apply all these rules of series circuits by considering two circuits below and completing some calculations around them. Here we have circuit A and we have circuit B. Circuit A and circuit B both have the same voltage of 2 volts. Circuit A has one 2 ohm resistor. Circuit B has a 2 ohm resistor and a 1 ohm resistor. That means that the total resistance of circuit B is greater than the total resistance of circuit A. Let's look at the current. Circuit A has a current of 1 amp. And circuit B, which has a higher resistance, has a lower current of 0.67 amps. And that makes sense because we just learned that as resistance increases, current decreases. What is the total resistance in circuit A? Well, in circuit A, we only have one resistor with a value of 2 ohms. So the total resistance is simply 2 ohms. And what is the total resistance of circuit B? Remember, you always have to show a formula, even if this formula seems kind of basic. So RT equals R1 plus R2, and we have two resistors. We have a 2 ohm and a 1 ohm resistor, so it's 2 plus 1, which gives us a total resistance of 3 ohms. So circuit B has a greater total resistance than circuit A. So from this, we can see that in a series circuit, the more resistors we add in series, the higher the total resistance. In any circuit, the voltage is provided by the cell. What is the total voltage in circuit A and in circuit B? We have to look at the value of the cell. We have 2 volts here, and we have 2 volts here. So the total voltage in each circuit is 2 volts. If I had to put a voltmeter across this resistor, what would the voltage reading be? There's one resistor, so this resistor is going to use up the entire voltage that's provided by the cell. So in terms of an explanation, we could say that the answer is 2 volts because there's one resistor, so it's going to use the full voltage that's provided by the cell. If you were asked to calculate it instead, well, you can apply the formula of V equals I times R. We want to know the voltage across the 2 ohm resistor. And we know that the current moving through the circuit is 1 amp. So the current moving through the resistor is also 1 amp. And I just want to make a very important note here that people tend to think that the current runs around the circuit and starts to bunch up at the resistor, kind of like it's being slowed down. But that's not the case at all. If the current is 1 amp throughout the circuit, that applies to the speed of the electrons as they move around the circuit. And at the resistor, they're not slowing down. They are still traveling with a current of 1 amp. The only thing is that they need more of a push to get through this obstacle course at the same speed, which is why the voltage is used across the resistor. So the current is 1 and the resistance is 2, and that would then tell us that the voltage across this resistor would be 2 volts. In circuit B, what would be the voltage across both resistors? Meaning that if I placed a voltmeter across both of these resistors, what would be the voltmeter reading? Well, in this case, it will also be 2 volts because remember that the total voltage in the circuit, which is provided by the cell, is 2 volts. And so how much voltage is available to both the resistors? 2 volts. So the 2 resistors in the circuit are going to use up the entire voltage that's provided by the cell. In order to calculate that, we can again apply this formula of V equals I times R. This time we need to use the current in circuit B, which is 0.67 amps throughout the circuit, and we need to use the total resistance if we want to identify the voltage across both of these resistors. To do that, we need to start off by calculating the total resistance. So that's 3 ohms. And now we may apply V equals I times R, which is 0.67 times 3, and we get an answer of 2 volts. Again, if we placed a voltmeter across both of these resistors, the voltmeter reading would be 2 volts, which is the same as the total voltage of the cell. Now, if we wanted to calculate the voltage reading across the 2 ohm resistor and the 1 ohm resistor, then we may calculate it again as V equals I times R, because we know that the current throughout the circuit is 0.67 amps, and across the 1 ohm resistor, the resistance is 1 ohm. So it would be 0.67 times 1, which would mean that the voltmeter reading across the 1 ohm resistor would be 0.67 volts. It takes 0.67 volts of energy to push the electrons through this 1 ohm obstacle course. To calculate the voltage across the 2 ohm resistor, we're simply going to apply the same formula, but for the resistance, we're going to use the value of 2. So it's 0.67 times 2, which is 1.34 volts. 0.67 volts across the 1 ohm resistor, 1.34 volts across the 2 ohm resistor. We can see that a greater voltage is needed to push the electrons across a resistor that has a greater value. Now just note that if I add 0.67 plus 1.34, I get a total voltage of 2.1 volts. There's a little bit of calculation error due to the way that I've rounded off, but that small calculation error is acceptable. There is another alternative for calculating the voltage across the 2 ohm resistor. That's because we have the total voltage and we've already calculated the voltage across one of the resistors, the 1 ohm resistor. Now what you'll find with circuits is that often there are many ways of calculating the same thing, and it doesn't matter which formula you apply. The alternative here is to say that the total voltage is equal to the voltage across resistor 1 plus the voltage across resistor 2. We know that the total voltage from the cell is 2 volts, and we just worked out that the voltage across the 1 ohm resistor is 0.67 volts. So the voltage across the other resistor would be 2 minus 0.67, which is 1.33 volts. Which of the two resistors has a higher voltage across it? Well, we already discussed this, and we said that if a resistor has a higher resistance, then it needs a greater voltage, and that's because the voltage is the energy required to move those electrons through the resistor. So the answer here would be the 2 ohm resistor, because the higher resistor requires a greater voltage because more energy is needed for the current to pass through a resistor with a greater resistance. It's like a harder obstacle course. In a series circuit, the current is the same wherever you measure it. So it doesn't matter if we place the ammeter here or anywhere else in the circuit. For circuit A, the current will always measure 1 amp. Prove the answer above by calculation. We can do that because we've got the voltage and we've got the total resistance. So if we have the voltage and the resistance, then we can work out the current as I equals V over R, which is 2 volts divided by 2 ohms, which is equal to 1 amp. What is the current throughout circuit B? Well, again, we can see the ammeter reading is 0.67 amps, and it doesn't matter where we place this ammeter. In a series circuit, the current is the same wherever you measure it. Now, again, if we want to prove this answer by calculation, then we need to apply the formula I equals V over R. To work out the current, which is the total current, we need to use the total voltage and we need to use the total resistance. So it is 2 divided by 3, which is 0.67 amps. In any circuit, the relationship between resistance and current is inversely proportional. And now we're going to explain this based on circuit A and circuit B. So what we can see is that in circuit A, the total resistance is 2 ohms and the current in the circuit is 1 amp. But in circuit B, where the total resistance is greater at 3 ohms, the current throughout the circuit is lower at 0.67 amps. And that is in line with our inversely proportional relationship between resistance and current. This brings us to the end of our discussion on series circuits. In the next lesson, we will look at parallel circuits.